So the third speaker in that session is Lennartsson. Kent Lennartsson and Lars Banner Fredriksson founded Kvaser in 1985 after developed 11-axis robot with distributed control, updated at 25 Hz using an RS-485 at 19.6 kilobit. Since 1990, Lennartsson has designed CAN and LIN interfaces with a common API for Windows and Linux. He has developed CAN FDAI IP used in several FPGA and ASIC products, and he is a member of the ISO 11898 committees, as well as the IEEE 802.3. And he also has been a member of the CIA since 1992. So can I please start your presentation?
So I will talk a bit about the CAN bus and the CAN bus layout and the CAN driver in cooperation with the bus. And it's all based on impedance variation because variation in impedance will distort the signal. So, but if you make the variation short, they will become invisible, and it's related to the wavelength in the communication. So if you have 1 megabit per second, typically 2.5 megahertz is the bandwidth you need, and that's 80 meters. So a drop with 8 meter will work fine. The problem is that if you have more drop lines, it will add up. So, and you can measure the impedance by the TDR, time division domain reflection, where you send in a signal. In this case, it's send it out. Let's see if I can get the cursor. The signal here in this point, and I send in the signal and see the impedance. And as you can see here, there is connectors here, and you see a small dip in the impedance here due to the cluster of connectors, and here another cluster that you will see here, and the end of the cable, it goes to infinity because there is no termination in this case. So next case, what we do here, we plug in some drop lines, short ones, a couple of meters, but you can see immediately that you get an effect. So you see here in the beginning, the impedance is correct. And when you have the first drop line here, you get a drop almost down to half the impedance, and then they come back again. But as soon as the signal reaches this point, it gets confused because this is also a violation for the impedance, and that messes up the whole thing here in the end. So it looks a little bit messy. So what happened is actually the signal here doesn't see if the drop line is where they go. So for the testing signal that you do the test, you can put the lines along in each other. And that's you can see that suddenly instead you have 100 ohm impedance, and suddenly you have two wires in parallel, which means that you get a half the impedance, 50 ohm. And that's why you get the drop here. And at the end here, it comes back to 100 because not only it's ending on the cable, but then you get the next group here with even worse because you have here 50, 1, 2, 3, 4, 5 cables in parallel. So the impedance actually drops to 20 ohm here, and which destroys the complete signal here in the measurement. And of course, if you make the full system here, typical automotive installation, you have longer drop lines and more complex drop lines, which makes that you can actually you can't measure the impedance because it's all messed up in the measurement. So we have to find another way to see the capability of this kind of networks. So what I do instead here is, instead of using a TDR instrument, I put this in a network analyzer so I get a transfer function from 16 to 17 here. And in this just straight line cable, you see that the energy is covering up to 100 megahertz here, but you have a start to get a drop here with 45 megahertz. So everything is perfect up to 45 megahertz where you get a 3 dB drop, but you can actually go above 45 megahertz, but you will lose half the signal. And if you put the drop lines here, you immediately see the effect of those drop lines, because the CAN bus signal, for a signal, this is like a low pass filter. And you can see here that it passes everything pretty good up to 45 megahertz when you have a huge drop in energy. Actually, it's a band pass filter because you get some energy here at a high frequency. So the full bandwidth, you only have up to 5 megahertz. And if you put in all the long drop lines, you see here that, that 5 megahertz now is at 3 dB. So actually, what you can go pass through here is 2.5 megahertz. So 1 megabit is maximum what you can pass through a network like this. And if we do the same measurement and scale oscilloscope, we get a clearer picture here. You see the up here to more or less 2.5, 3 megahertz. It's a straight line, and you get the phase shift here. But at 4 megahertz here, you can see you have lost half the signal. So you have to have the energy. You can only get energy up to 2.5, 3, some up to 4 megahertz. So the problem here is, of course, that you have to check from every source to add all the ends. As we have seen before, that the failure you have depends on where you connect it. So you actually have to do the same measurement here as many times as you have positions, and you have to put the source at different location as well to find the worst cases. With some experience, you learn where to look, and in this case, the worst drop we actually have from 16 here to this drop line. It's even worse than to those end for some reason. And in this case, you can see here that you can reach up to 2 megahertz, and with already with 2.8 megahertz, you have lost 50% of the signal. So in this system, you have to stay below 1 megabit to get a good useful CAN communication. And the reason I say in this is that if you, I think in this case it used 500 kilobits per second. And what we do here, because the previous measurement here, the TDR and the S12 measurement is based on sinus signals. So, and of course, when you do the CAN communication, we have binary signals. So if you take 500 kilobit per second, and the worst case you can have is the sequence 010101. And that's a square wave 250 kilohertz. And what you can do here is you Fourier transformation of this 250K signals to get the components in energy. And you can see here the frequency, the basic, of course you get 250 kilohertz, but then you get 750, 1250, and it's in step here actually in 500 kilohertz. But on the other hand, you can see that you need a lot of power in the first baseband, 250K, but very soon the power demand to recover the square signals reduces a lot when you get to high frequencies. So actually, to recreate this kind of CAN signals, you need roughly the 3 first, possibly the 4th as well. So let's go and look into a real signal. So what we have here is the input signal in one end in this simplest bus system, and we have a 5 nanosecond slow rate here, So the only problem we see here is, of course, the delay through the bus, the signal delay from one end to another. And if you look at the spectrum, we have this source here in this end, and we look at the energy here. You can see you have the peaks here with 250, 750, and the same as you had in the table below. And you can see how the energy drops by the frequency. So the easiest way here to get a nice good looking signal is to reduce the slow rate. So in this case, I reduced the slow rate from 5 nanoseconds from the switching to 200 nanoseconds. And as you can see here in the energy, when we measure the energy in the end, you get the first spike here, but then the slow rate makes you need less high energy. And the energy you see up here is actually from the corners up here. So if you have a CAN driver that can reduce the corners here, you get rid of this high frequency energy as well. So this is the energy you will see in the cable by 5 nanosecond slow rate. And this is the energy at 200 nanosecond slow rate. So just by changing the slow rate, we have a huge effect on the energy that you send out on the bus in high frequencies and the demand of the cabling system. So you can see here that the 750 kilohertz signal here compared to this signal here, due to the slew rates, only 0.2 dB lower, and the next is 1 dB lower. And of course, all the others are up here, it's much lower than you get with the high slow rate signal. So again, we can see here, this is with a high slow rate signal, and if this simple system, of course, it's no problem here. So the only thing you have is the delay. And when you go to the high slow rate, it's perfectly well for CAN communication. And of course, you get the same delay here as well, because even if you change the slow rate, you still have the delay in the cabling system. If you make the complex network here and put in the signal here, you can see the reflection. So the signal goes here, and you put a lot of energy, and you get reflections all over here. And after some time, it recovers in the sender end. It's 16 here, but as you can see here in 17 here, you don't see this, because it's only happened here is because this works at the low pass filter. So it's all this energy you have here disappears. So you get a signal with a slower slow rate. And if you switch from the 5 nanoseconds here to the 200 nanoseconds, all the problems disappears. So what we have seen so far is S12 measurement, and where we have a perfect matching of both both ends. So it's impedance match source and it's impedance match receiver. So it's a perfect installation, and that's not true because if you look at the CAN bus, it has a CAN driver doesn't have impedance match driver, and the termination is not located exactly at where the CAN drivers are installed. So what happened here is that this is a signal you get when you have a perfect match of the impedance in both ends, and this is the real signals that you have in the CAN driver. And this is high slow rate, and here the CAN driver it's not 5 nanoseconds, it's like 20, 30 nanoseconds. And the dip here you get is actually is due to the reflection to the CAN driver, which doesn't have a perfect impedance match to the cable. So you get a reflection from the source. When the energy, you send out energy here, and you get reflection both here and here. And when the energy comes back here, it will be reflected due to the CAN drive doesn't match the 100 ohm impedance. And of course, you have an even worse cases in the recessive edge, because there is no driver who can burn away that. It's all relying on the termination, which is not located in the correct location. Still, this is a pretty good bus. As you see before, where the NXP measurement, their networks was much worse than this, but they are also using higher bit rates. So the complication for CAN drivers is asymmetric signaling that you necessary. You have dominant and you have recessive bits, which makes it complicated to make a good signaling, because to get a good symmetry, you would like to drive the signals in both directions. And this is partly solved with a SIG transceiver, where you at least you drive the edges, even if you don't drive the whole bit. You actually, the switching is done by the SIG, like the SIG transceiver. So you get a better symmetry between making the bits dominant compared to making the bits recessive. And another factor is that the CAN bus will always be imperfect. It will never have a straight cable, simple impedance from one end to the other, because if you have a CAN bus, you need to install the modules in a multi-drop location, and each such connection point will do some imperfection in impedance and cause reflection that will make the bus signal don't be as good as you would expect in a real standard point-to-point data communication. So the first thing you should do is to make life easy for the CAN drivers. And that is to make the CAN bus as good as possible. And to do that, the easiest way is to make the short drop lines, short as possible. As you see before, it's pros and cons. In some cases, you need to have the drop lines to have a proper cabling, because for weight or location constraints, you cannot get the cable wiring back and forth to find all the ECUs. So sometimes you have to have drop lines, but at least you should make the drop lines as short as possible to minimize the reflection that you will get from when the signal reaches the drop line. And you should also, another time you put a lot of capacitors and inductive loads in the ECUs for EMC reasons, but those active components, passive components with storing energy can make it complicated to analyze and understand where the energy comes and goes. So if you get away with the capacitance and inductive load in ECUs, it will be easier to understand the behavior of the CAN bus. And you should use a termination that match the cable. So actually this historic reason to have 120 ohm is perfect if the cable is 120 ohm. But if you use like a Cat5 cable, a twisted pair, it's 100 ohm impedance. And in that case, a 100 ohm terminator is a better use than 120 ohm. And then the next problem, of course, is to use a cabling with an impedance variation that is very low, so it doesn't change by temperature and time. And like PVC is isolation material that change the impedance dramatically at low temperature, and that could be a problem, and has to be tested at least that your cabling, your system is still working with a cold cabling system. So you can do a lot with the CAN drivers, but there's no reason not to optimize the CAN bus system as such before you try to buy expensive CAN drivers to solve the problems you have made yourself by making a bad CAN bus layout. So to me, the improved CAN drivers should have adjustable slow rate. There is some CAN drivers with adjustable slow rates, but there are fewer and fewer, and a lot of them are more into increase the slow rate to handle the higher bit rates. But if you want to go to lower bit rates, it's much better to reduce the slow rate that match to your network, because if you have a complex network, there's no reason, as we see from the measurement here, to put a lot of high energy, high slow rate into the bus layout, because it will anyhow be filtered out by the bus layout, and it's just a waste of energy. So the best is to match the slow rate to your CAN bus layout and use as low slow rate as possible so you don't force into oscillation. Because if you don't have an energy, high energy, there's no way it can oscillate at high energy either, high frequency. And it's also good if you have an adjustable output impedance or have a cable. The CAN drivers today have typically an output impedance of 10 to 20, 30 ohm, and that's not very suitable to drive the bus. So, and I heard here from the presentation, I think on Monday, that actually I think it was in Finland, their drivers will actually have a 100 ohm impedance, which will make them more matched to the cable and reduce the reflection during the sending situation, when you get feedback energy back from your drop lines. And of course, as I saw before here, is necessary also to make sure that the CAN driver have rounded corners that match the slow rate, because if you have sharp corners, they will also cause a high energy out from the sender, which will be causing high frequency ringing when it reflected into the drop lines. So that's my presentation.